There are several issues related to the operation of aerial robots in uncertain environments. First of all, their control is challenging due to the involved nonlinearities and intercoupling. Moreover, their control by model-based controllers requires a precise modeling of the system, which is time-consuming and involves a number of repeated experiments. Besides, there may be underlying internal uncertainties which may affect the model parameter values or external uncertainties comprising of time-varying disturbances. Hence, in this paper, we propose a simple learning strategy to make the traditional feedback linearization controller adaptive to the changing operational conditions. In the proposed control framework, FLC is responsible for position tracking. That is, after receiving a position reference, it commands attitude angles as well as throttle to the low-level controller, which further gives the actuator commands to the UAV. Now, to make the high-level FLC adaptive, the simple learning strategy minimizes the desired closed-loop aerodynamics via the gradient descent method in order to obtain the new adaptation rules and the disturbance estimate. These obtained values are then updated within the feedback control law and the whole process is repeated. The experimental validation of the control framework is done with the help of 3 case scenarios, the first amongst which is the mass variation. In this scenario, the UAV tracks an H-shaped trajectory while disturbance in the form of payload drop is induced once per lap. As seen from the results, Z error for the traditional FLC rises with each drop, whereas the SL algorithm in SLFLC framework learns the change in mass, hence able to maintain the Z error down to the minimum. The second scenario involves the introduction of ground effect disturbance. In this experiment, the UAV tracks a circular trajectory involving 2 heights, wherein the ground effect disturbance is experienced when it flies in proximity to the ground. As observed from the results, the SL strategy is able to learn the reduced mass due to ground effect and hence maintains the Z error to the minimum. On the other hand, the Z error for traditional FLC always rises in the presence of ground effect. The third scenario involves the introduction of wind gust disturbance. In this experiment, the UAV tracks a hover trajectory with sinusoidally varying height while in the presence of wind gust disturbance, which is induced with the help of 2 industrial fans. As seen from the results, the SLFLC framework is able to estimate the induced disturbances and thus produces lower Euclidean error as compared to the traditional FLC method. To conclude, in this work, an SLFLC algorithm has been proposed for the control of nth order uncertain systems. The desired closed-loop aerodynamics is ensured in the presence of matched and mismatched disturbances. The performance of the traditional FLC and SLFLC framework is experimentally evaluated for 3 different disturbance scenarios. The experimental results illustrate a superior tracking performance by the SLFLC framework over the traditional FLC method. For more details, please refer to the paper.